Imagine you hire like a new research assistant, and not just any assistant. We are talking about a top-tier recruit, absolute top of their class, a total genius on paper.
Right, the kind of hire you're really excited about.
Exactly. So you give them this really complex project to prep for a crucial meeting you have coming up, but instead of actually going to the library or, doing a basic web search to find the most up-to-date data, they sit at their desk, stare at the wall, and confidently hallucinate the answers.
Which is completely useless.
Right. Or worse, they go to the library, look up the exact same book 50 times in a row, and then hand you a blank piece of paper. In the real world, you'd fire them on the spot.
Oh, absolutely, without hesitation.
But that exact measurable structural failure is happening right now in the state-of-the-art AI systems running on millions of our devices.
Welcome to today's deep dive, everyone. Yeah, it is a sobering reality for the tech industry right now. Because, we're rapidly moving past the era of simple chatbots that just fetch a single piece of trivia for you.
Right, we're asking them to do actual work now.
Exactly. We are starting to rely on these autonomous agents to navigate the live web, synthesize massive amounts of conflicting data, and, actually solve multi-step problems on our behalf.
Yeah.
But if the fundamental logic engine driving them gets lazy and just stops searching for the truth, the whole system collapses.
So today, our mission for you, the listener, is to figure out why the most advanced AI agents in the world develop these incredibly frustrating behaviors. And more importantly, how scientists are fundamentally rewiring them to actually learn.
We've got a really fascinating stack of sources to get through today.
Yeah, we are looking at this brilliant YouTube video breakdown of an October 2025 University of Virginia paper. We've also got a really revealing March 2026 interactive AI study. And on top of that, a brand new March 2026 research paper, complete with its raw visual data on a groundbreaking framework called XSKILL.
And, the through line connecting all of this research is that developers are finally diagnosing the actual psychology of artificial intelligence.
It's the psychology of it, yeah.
Because before we can fix complex multi-step logic loops, we have to look at how we train these models in the first place. For years, the industry standard has been this method called outcome-only reinforcement learning.
Okay, let's unpack this. What does outcome-only learning actually look like when an AI is being built?
Well, it basically means the AI is evaluated using a strict exact match reward at the very end of a task. Let's say the AI has to execute a dozen complex steps.
Like formulating a search query, scraping a website, that kind of thing.
Exactly. It needs to filter out the noise, synthesize a paragraph of text. Under outcome-only learning, the system doesn't care about any of that middle work. It just checks the final output against an answer key.
Oh, wow. So no partial credit at all.
0. If the final word matches perfectly, the AI gets a 1. If it misses the final word, it gets a 0. There is 0 partial credit for using the right tools or, finding the right website.
Okay, so if I'm understanding this, is this basically like trying to teach someone how to bake a complex multi-layered cake, but you only ever grade the final taste?
That's actually a great way to think about it.
So they get like a massive red F on the assignment, but they have absolutely no idea if they failed because they swapped salt for sugar in step 2, or if they just completely forgot to turn the oven on in step 4.
That analogy captures the frustration of the system perfectly. The AI is essentially forced into a state of blind guessing. It tries to figure out what went wrong on its next attempt without any feedback on its methodology.
Which sounds incredibly inefficient.
It is. And when you scale that kind of blind guessing across a model with billions of parameters, the AI develops highly neurotic habits to try and game the final score.
Neurotic habits. What does a neurotic AI actually do when it's trying to game a search task?
Well, the researchers at the University of Virginia actually quantified this phenomenon. They tested the Quinn 2.5 models, both the 3 billion and 7 billion parameter versions, and they identified 3 specific deficient search behaviors.
Okay, what's the first one?
The first behavior is called calls fail to search. The AI basically calculates that searching takes computing effort, so it bypasses the search tool entirely.
Wait, it just doesn't search at all?
Nope. It just hallucinates an answer from its outdated internal memory, hoping it gets lucky and hits that exact match reward.
Which is terrifying if you are relying on that agent to pull real-time data like a livestock price or breaking news.
Exactly. Then the second behavior is almost the opposite extreme: duplicate queries.
Oh, I think I've seen this happen.
Yeah, the AI recognizes it lacks the information to answer the prompt. But because it never received feedback on how to actually refine a search term, it just searches the exact same broad keyword 50 times in a row.
So it's just spinning its tires in the mud.
Exactly, getting stuck in an infinite loop, burning massive amounts of computing power without ever narrowing down its investigation.
Man, that's wild. What's the third behavior?
The third is perhaps the most catastrophic. They call it invalid searches. The agent literally mashes the keyboard.
Like a toddler playing with a laptop.
Pretty much. It will output broken Python code, mismatched HTML tags, or just strings of meaningless punctuation directly into the search bar. It has learned this vague correlation that using the search tool sometimes leads to getting a point, but it has no idea how to actually format the input.
Those sound like catastrophic bugs. What does that actually do to the model's performance numbers?
The data is pretty grim. When these deficient behaviors kick in, the AI's recall rate, which is its mechanical ability to pull the right document from a database, plummets to 43.2%.
Ah, that's terrible.
And because it can't find the documents, its final accuracy drops from a baseline of 52% down to an abysmal 19.7%. It represents a total failure of the training curriculum.
Wow. So how do we fix this lazy assistant?
To fix this, the UVA team introduced a framework called DESA, which stands for decoupling search and answering. They recognize that searching for data and synthesizing a final answer are two entirely different cognitive skills, so they split the training process in half.
Wait, I have to jump in and push back on this architecture a bit.
Sure, what's your thought?
If an AI is supposed to be this hyper-efficient processing machine, wouldn't it be easier and honestly way less computationally expensive to just train both of those skills at the same time? Like, why not just rewrite the reward function so the AI gets a half point for retrieving the right document and another half point for getting the final answer right?
You'd think so, right? But the researchers actually tested that exact simultaneous hybrid approach, and it failed entirely due to a phenomenon called confusing optimization pressure.
Confusing optimization pressure?
Yeah, if the two skills are trained together, the AI relies on the mathematical path of least resistance. It figures out that it is computationally cheaper to secure the final answer half point by guessing from its internal memory, rather than expending the energy to master the complex mechanics required to earn the search half point.
I see. The optimization pressure pushes it toward laziness.
Exactly.
So you have to force the system to master the knife skills of chopping ingredients before it is ever allowed to touch the stove.
That's it exactly. DESA forces that isolation. Stage one is pure search acquisition. The final answer key is thrown out completely. The AI is trained purely on the physical mechanics of investigation using a recall reward, which only checks if the underlying factual keywords were pulled back in the search dump.
Okay, and once it masters that,
Once those search pathways are solidified, it graduates to stage two, outcome optimization, where it finally learns to synthesize the answer. By decoupling the pressure, those deficient keyboard mashing searches drop from over 23% down to just 6.96%.
that is a massive improvement. So DESA fixes the AI when it's executing a single Google search to find one right answer.
Right.
But real-world problems aren't usually a single step.
Right.
Like, if you are using an AI to debug a massive software code base or to diagnose a patient's symptoms, your second search depends entirely on what you found in your first search. It is highly interactive.
Very true.
And this brings us to the March 2026 study in our stack. What happens to the AI's logic when the environment becomes interactive?
It breaks down in a completely different way. Real-world, multi-turn environments introduce a deeply psychological flaw that the researchers call information self-locking.
Information self-locking. That sounds ominous.
To understand why this happens, the study defines the two pillars of interactive AI. The first pillar is action selection. These are the outward actions the AI takes, like asking a database a question or running a line of code.
Okay, got it.
The second pillar is belief tracking. This is the internal updating of the AI's running hypothesis based on the new evidence it just gathered from its action.
Okay, let me make sure I'm mapping this correctly. Is this basically like a detective working a homicide case?
Yeah, let's hear it.
So action selection is the detective physically going out and interrogating a suspect. And belief tracking is the detective coming back to the station, looking at the corkboard, and updating their theory of the crime based on the suspect's alibi. So does the AI just, like, decide who the killer is in the first 5 minutes and stop looking for clues?
Exactly. That perfectly illustrates the dual process. In standard reinforcement learning models, those two pillars cannibalize each other in a toxic negative feedback loop. The AI stops updating the corkboard.
How did they actually prove that?
The researchers proved this using the Metacheek dataset. which is a highly complex medical diagnosis simulation. They had the AI play doctor asking a simulated patient a series of diagnostic questions.
Okay.
Halfway through the session, the researchers intentionally intervened. They hid all of the patient's feedback, and the system just started returning the word unknown to every single question the AI asked.
Wait, if that happened in reality, a human doctor would immediately stop the exam and say, something is wrong, I can't hear you, I need more information before I can make a diagnosis.
Exactly. But the AI didn't care at all. The telemetry showed it had a 92.8% belief consistency. It stubbornly stuck to its initial hypothesis from the first few minutes of the simulation, regardless of the fact that it was receiving zero new information.
It just completely ignored the fact that the patient went silent.
Yep. It was going through the outward motions of action selection, asking the patient questions, but its internal belief tracking was locked tight. It developed a form of multi-turn amnesia.
So how do you cure a stubborn digital detective? Do developers have to throw out the entire model and retrain it from scratch?
Fortunately, no. The study brings up a minimalist intervention they call advantage reweighting, or ARW.
Advantage reweighting. And the paper says it assigns a +1 for good informative queries and a -1 for bad duplicate ones. But I have to admit, I'm completely stuck on the logic here.
Why is that?
Didn't we just establish that mixing points and rewards is exactly what confuses the AI and makes it lazy? Want to just reward hack this new system, ignore the patient entirely, and just spam random questions to rack up +1s?
What's fascinating here is the underlying math. It's a crucial distinction because ARW avoids that exact trap. They aren't altering the reward function, which, to use our earlier analogy, is the final exam grade. They are modifying the advantage function.
The advantage function, how is that different?
The advantage function is the internal, real-time metric the AI uses during its study sessions to evaluate the quality of its own habits. The researchers describe ARW as a zero-sum gradient scalpel.
A zero-sum gradient scalpel, that sounds incredibly intense. How does a gradient scalpel actually work in practice?
Think of it like a master volume slider on a soundboard. ARW doesn't create any new points for the AI to hoard or game. Instead, it looks at the mathematical probability that the AI will repeat a bad habit, like ignoring patient evidence or asking a duplicate question.
Okay.
It takes that probability mass and it slides the volume down. Then, because it is zero-sum, it takes that exact same probability mass and pushes the volume up on curiosity and information-seeking behaviors.
Oh, wow. So you aren't changing the final score of the test at all. You are reaching into the AI's brain and just turning up the volume on the study habits that inevitably lead to passing the test. And this one tiny mathematical tweak cures the amnesia.
It drives massive improvement. That single mathematical adjustment yields up to a 60% performance boost across complex interactive datasets. The AI goes from being a stubborn liability back to an aggressively curious investigator that actually listens to the evidence.
Okay, so we have established how to fix logic loops in text-based environments. We stop them from being lazy with DESA, and we cure their stubborn amnesia with ARW.
Right.
But the AI world is moving incredibly fast. What happens when the AI steps out of a clean text box and has to navigate the messy, unpredictable, visual world of images and video?
Oh, this is the massive frontier right now. Multimodal agents, AIs that can see and process images, suffer from terrible tool inefficiency. When they operate in the wild, their logic orchestration becomes incredibly inflexible.
Why is the visual world so much harder for them?
Because visual problem solving requires two completely different types of memory operating at the same time. This is the breakthrough detailed in the March 2026 XSKILL paper.
Ah, the dual-stream memory framework.
Exactly. The researchers built a dual-stream framework to hold both forms of knowledge simultaneously. The first stream is called skills. These are stored internally as markdown documents. They represent task-level, highly structured workflows.
So like a step-by-step guide.
Right. They provide the rigid syntax and the technical blueprints, which stops the AI from wasting steps on basic formatting errors when using a tool. The second stream is called experiences, which are stored as lightweight JSON files. This is the action-level, context-sensitive tactical knowledge.
Okay, let me try to map this to the physical world. Is this dual stream system like the difference between reading a textbook on how to ride a bike versus the actual tactical experience of writing one?
That's a great way to look at it.
Like the markdown document is the structured textbook. It tells you to put your foot on the pedal and push. But the textbook cannot tell you what to do when a stray dog suddenly runs in front of your front tire. The JSON file is the instinct to swerve because you've experienced that chaos before.
That is the exact division of labor. The structured workflow prevents you from putting your hands on the pedals instead of the handlebars. The experiential knowledge allows you to navigate the unexpected dog.
But how does a neural network actually accumulate real-world tactical experience?
The XSKILL framework achieves this in two distinct phases. Phase 1 is accumulation. The AI performs multiple rollouts or attempts on a visual task. Then it uses a mechanism called cross-rollout critique.
Cross-rollout critique.
Yeah, it doesn't just look at a failure in isolation. It explicitly puts its successful trajectories side by side against its failed ones. It analyzes what specific visual evidence motivated a correct tool choice and saves that nuanced insight into its JSON memory bank.
It's actively contrasting its own history to find the variable that led to success.
Exactly. Then comes phase 2, inference. When the AI faces a brand new visual problem, it uses task decomposition retrieval.
Which means?
Instead of following a rigid prescriptive rulebook, it breaks the new image down, retrieves relevant tactical experiences from its JSON files, and dynamically writes its own custom system prompt based entirely on the unique visual context it's currently looking at.
Here's where it gets really interesting, because looking at the actual visual evidence provided in the XSKILL paper makes this abstract process click instantly.
The image tests are wild.
Yeah, let's look at the mascot image test they ran. The user provides a picture of a street corner, and there are two mascots visible. The prompt asks the AI to identify the original prototype of those mascots.
Right, but there's a huge trick to it.
Exactly. The massive catch is the image provided is totally upside down. If you feed an upside-down image to a standard baseline AI, what does it actually do?
It fails completely. The baseline AI blindly follows its rigid workflow. It tries to draw a bounding box and crop the upside-down image, gets completely confused by the inverted pixels and lighting, and ultimately fails to identify anything meaningful.
But an AI equipped with XSKILL handles it differently.
Entirely differently. The XSKILL agent analyzes the image and retrieves a specific visual experience from its JSON memory bank. It recognizes that the image is inverted. It realizes that before it can analyze the mascots, it has to fix the orientation.
Like, really? It actually realizes it's looking at the world upside down.
Yes. It pulls a markdown skill template to execute a block of Python code, physically rotates the image 180 degrees in its workspace, realizes the mascots are still too small to see clearly, zooms in with a precise secondary crop, runs a visual web search, and correctly identifies that the prototype of the mascot is a bird.
A bird, and the baseline model couldn't even get close.
The baseline model, if it guessed at all, might have hallucinated a dolphin. XSKILL used its experience to manipulate the environment before solving the problem.
That is incredible. There is a second visual example in the paper that really blew my mind. It's a picture of a bustling street scene, and there is a taxi cab driving by with an advertisement on the side that says, "Good gifting, good values."
Oh, the taxi ad test.
Yeah. The prompt asks the AI, "In what color area is the second good text on the car body located?" A standard baseline AI looks at the overall car and guesses red.
Which is an easy mistake to make if the AI is just glancing at the overall ambient hue of the advertisement and the surrounding streetlights. But XSKILL doesn't just guess.
Right.
It retrieves a specific tactical experience for dealing with ambiguous lighting and small text. It initiates a process called systematic scan and forensic pixel sampling.
Forensic pixel sampling. What does that mean for an AI?
It means it stops relying on generalized visual assumptions. It isolates the exact region of interest around that specific second word. It objectively measures the underlying RGB values of the pixels surrounding the letters, filters out the ambient light distortion, and correctly identifies that the true background color is purple.
It's not just looking at the picture. It is applying the scientific method directly to the pixels.
Exactly.
And the paper highlights an amazing implication of this dual-stream architecture. This accumulated knowledge isn't permanently locked to the specific massive model that learned it, is it?
That might be the most powerful finding in the entire paper. Because the knowledge is externalized into human-readable Markdown and JSON files, it is completely portable.
So you can just move it around?
Yep. A highly capable, massive model like Gemini 3 Flash can spend hundreds of hours accumulating this deep visual tactical knowledge. Developers can then simply export those files and plug them into a much smaller, more efficient model like GPT-5 Mini or a 4 Mini.
Oh, wow. So you instantly upgrade the smaller model's visual problem-solving skills without spending millions of dollars and massive amounts of energy retraining its neural weights from scratch.
Exactly. It's plug-and-play experience.
So, what does this all mean for you, the person actually using these tools? As we hand over increasingly high stakes tasks to autonomous agents, whether that is an AI managing your financial portfolio, an agent debugging critical software infrastructure that runs your business, or a system diagnosing complex medical symptoms for your family, we simply cannot afford for them to be lazy.
We really can't. The stakes are getting too high.
Right. We cannot afford for them to suffer from stubborn detective syndrome the moment they encounter a confusing visual or textual roadblock. The frameworks we've explored today, DESA, advantage reweighting, and XSKILL, aren't just neat academic tricks. They are the fundamental guardrails keeping AI curious, adaptable, and tethered to the reality of the real world.
And, if we connect these breakthroughs to the bigger picture, it raises a deeply provocative question about where we are heading next.
Ooh, what's that?
Both the YouTube video's analysis of search behaviors and the XSKILL paper look at single AI agents trying to find the truth in isolation. But the future of this technology is multi-agent systems.
Right, multiple AIs working together.
Exactly. Imagine putting two stubborn, self-locked AIs in a digital room together to solve a massive engineering problem. Will they just argue endlessly, talking past each other like stubborn human debaters who refuse to update their corkboards?
That sounds like a nightmare.
Or could developers use these very same tools, like that zero-sum gradient scalpel, to train AI agents to psychoanalyze and cure each other's self-locking behaviors in real time, creating a self-healing digital ecosystem?
Wow. An autonomous AI therapy session for stubborn digital detectives. That is definitely something to mull over as these systems become more integrated into our lives. Thank you for joining us on this deep dive. Keep an eye out for those lazy assistant behaviors in the AI you use every day. And remember, just because an agent gives you a confident answer in 3 seconds doesn't mean it didn't just stare at the wall and hallucinate the whole thing.